Hello friends, today we'll continue with comparison test 2, which is also known as quotient test for the convergence of the improper integrals of type A. Okay, we will see first statement. Okay, so comparison test 2, comparison test second. This test also known as quotient test. Okay, now we will see the statement of this test. Okay, so the statement is, so there are two functions, function f and g, both are non-negative, that is greater equal to 0. Okay, and there is some element x which is greater equal to a. Let limit x tends to infinity of the ratio of two functions f of x upon g of x. This ratio also known as quotient. So this test also has a name quotient test. Okay, suppose limit as x tends to infinity of the ratio of a function f of x upon g of x is equal to say L. Okay, now depend on this L. Okay, if this L is positive real number, okay, and L is greater than 0 real number, okay, then the improper integral of the function f and the improper integral of the function g from a to infinity both converge or diverge together. Okay, if this limit is greater than 0 and a real number, then these both improper integral convergent or divergent together. Okay. Second case is, if L is equal to 0. Okay, then if the improper integral of g of x is convergent, then improper integral of f also convergent. If the improper integral of g is convergent, then the improper integral of f also convergent. And third case, if this limit L is equal to infinity, then if improper integral of g from a to infinity is divergent, then improper integral of a to infinity of f also divergent. These are the three cases in this comparison test 2 or quotient test. What this test says, if there are two non-negative functions and we have a limit of ratio or quotient of f upon g, and limit of this ratio is say L. If L is positive real number, then the both integrals converge or diverge together. If limit is equal to 0, then if the improper integral of g is convergent, then improper integral of f also convergent. If limit is equal to infinity, then if improper integral g is divergent, then improper integral of f also divergent. Okay, this is the comparison test 2 or quotient test. Okay, friends, now we will see the example based on this comparison test 2 or quotient test. So we have to test the integral 0 to infinity of x upon square root of x cube plus 1, okay, with respect to x. So we have to check whether this integral, this improper integral, we know because limit is infinite, so we have to check whether this improper integral is convergent or not. Okay, now we will use here the comparison test 2. So here our function is x upon square root of x cube plus 1. We will give its name function f, say. Okay, so here we have given function f of x is given, it is x upon square root of x cube plus 1. This is our function f. But for comparison test 2 or quotient test, we need another function g, and we have to take the ratio of limit of function f and g. Okay, so what we will do, we will find the function g. Now I will give some clue or idea to how to find another function g, so it will help us to find the limit of the ratio. So the general idea in this test to find the function g is, so take the function g of x equal to 1 upon x raised to power. Look, however, I am constructing the function g. I am taking the ratio 1 upon x raised to power, highest power of x in denominator. What is the highest power of x in denominator? Square root of x cube, na? So x raised to power 3 by 2. This is square root. So x cube plus 1 raised to power 1 by 2. So highest power is x raised to power 3 raised to power 1 by 2. So x raised to power 3 by 2. Highest power of x in denominator minus highest power of x in numerator. What is the highest power of x in numerator? Is 1. So 3 by 2 minus 1. This is equal to 3 by 2 minus 1 is 3 minus 2, that is 1 upon 2. So 1 by 2. So take g of x is equal to 1 upon x raised to power 1 by 2. This is one way to find the function g. So we will use this function. Okay. So our g of x is 1 upon x raised to power 1 by 2. Okay. Now we will find the value of limit x tends to infinity of f of x upon g of x. Okay. This is equal to limit x tends to infinity. What is the f of x? F of x is x upon square root of x cube plus 1. Okay. And now this is our f upon g, and our function g is 1 upon x raised to power 1 by 2. So, but instead of writing in denominator, when we write in numerator, we have to change the numerator and denominator. So this we write this as into function g of x is 1 upon x raised to power 1 by 2. So when it goes to numerator, it become x raised to power 1 by 2 upon 1. So just x, this function as it is, this is x raised to 1 by 2 upon 1. So it is just x raised to power 1 by 2. But x into x raised to power 1 by 2 is nothing but x raised to power 3 by 2. Okay. So this is our function f upon g. So we have to calculate the limit of this f by g as x tends to infinity. This is equal to limit x tends to infinity. Okay. Now x raised to power 3 by 2 means x raised to power 3 raised to power 1 by 2. So 3 into 1 by 2 is 3 by 2. Okay. So this is the square root of x cube. This is nothing but square root of x cube. X raised to power 3 by 2. So x raised to power 3 raised to power 1 by 2. So x cube raised to power 1 by 2. So square root of x cube. This is nothing but square root of x cube. Okay. Or we can write this like square root of x cube. Okay. We will write this as square root of x cube upon square root of x cube plus 1. Now we can take this square root of x cube outside the this square root. Okay. Now this become limit x tends to infinity, this square root of x cube as it is in the numerator. In the numerator we can write, we can take this square root of x cube outside. Okay. So square root of x cube. So here what remains in the bracket? In bracket it remains square root of 1 plus, now here there is no value, we have taken just square root of x cube outside. Okay, but here there is no x cube, so here it will be 1 upon square root of x cube, so x is to power minus 3 and this square root as it is. Okay, or we can write it as 1 upon x cube in the square root. Okay, why? Because when this square root of x cube come inside, so square root of x cube into 1 x cube, and when this come inside, so x cube, so square root as it is, x cube into 1 by x cube get cancelled, so remains only 1. So this is just some adjustment. Okay, now this gets cancelled, and as x tends to infinity, 1 upon x cube tends to 0. So this tends to 1 plus 0 is 1. Here remain only 1. So 1 by 1 is 1. So limit is 1. Okay. So limit of f upon g as x tends to infinity is 1. It is a positive real number. So by comparison test, both function f and g and then improper integrals of both function f and g converge or diverge together. But okay, so by comparison test 2, so by CT2, both the integrals of f and integral of g from a to infinity converge or diverge together. Okay, but the improper integral of g, okay, but the improper integral of g, that is 1 upon x to the power 1 by 2 from 0 to infinity. Okay, here 0 to infinity, 0 to infinity. Now we know with respect to dx. Okay, now we know the improper integral dx upon x to the power p is convergent when p is less than 1, and here p is 1 by 2. So here 1 by 2 is less than 1. This implies this improper integral is convergent. Okay, our test says both the improper integral converge or diverge together, but improper integral of g is convergent. So improper integral of f also convergent. This improper integral is convergent by comparison test 2. This implies improper integral from 0 to infinity of x upon square root of x cube plus 1 is convergent. Why it is convergent? Because improper integral of g is convergent, and our test says if limit is non-zero real number, then improper integral of f and g converge or diverge together. But improper integral of g is convergent by test integral. We know integral of dx upon x to the power p is convergent when p is less than 1, and here p is half, which is less than 1. So by test integral, we know this integral of this 1 upon x to 1 by 2 is convergent. So improper integral of this also convergent by comparison test 2 or CT2 or constant test. Okay. So the next test for the criteria of checking the convergence of the improper integrals of type A is the limit test of convergence. Okay. So the name suggests we have to take limit of something. Okay. So test is, suppose there is a function f of x which belongs to the class of continuous functions. X is the element which is greater equal to a and finite, so less than infinity, and limit x tends to infinity of, so you are take limit test. Okay, and limit x tends to infinity of x to the power p into f of x is equal to, say, L. What is L? L is the limit of x to the power p into f of x. Okay, now if this p is greater than 1, okay, and this limit of this x to the power p into a function is real number, then the improper integral of f converges absolutely. Okay, now if p is equal to 1 and limit is equal to infinity plus or minus or not equal to 0, p is equal to 1, limit is equal to plus minus infinity, not equal to 0, then the improper integral is divergent. Okay, and the test fails for n is equal to 0 and p is equal to 1. Okay, so if we have example and they say we will check or show that this improper integral is divergent using limit test. So for showing or checking whether the integral is divergent or not, we have to, for divergent, we have to take the value of p is equal to 1 and check the limit of x is to power p is equal to 1. So limit of x into x is equal to L, and if limit is equal to infinity plus or minus infinity not equal to 0, then integral is divergent. But if they say to show the integral is convergent, then we have to take the value of p greater than 1 and then check x to the power p into f of x, this limit is real number, then the integral is convergent absolutely. Okay. This is the limit test of convergence. Here this test is based on the value of p and the value of this limit of this function. Okay. So we will see example based on this test, so your idea will get clear. Okay. Now we have given two examples. So in the first example, the question is, show that the integral 1 to infinity of x square minus 1 upon x square plus 1 dx is divergent. Okay. And in second question, we are asked to show that this integral x square into e raised to minus x square is convergent. Okay. So we will first solve this example. Now you have to use limit test here. Okay. So they have asked to show that this integral is divergent, and we are going to use limit test. Now we have seen in limit test to show some improper integral is divergent, we have to take the value of p is 1. So x is to the power p into f of x and limit x tends to infinity. Okay. So we will take this is our function f of x. So limit x tends to infinity, x is to the power p, but we have to show integral divergent, so we have to take p is equal to 1. So x is to the power 1 is x into f of x. What is f of x? This x square minus 1 upon x square plus 1. But before that, the criteria of limit test is that function must be continuous on the given interval. Now here this function x square minus 1 upon x square plus 1, it is continuous from 1 to infinity. There is no singular point. Okay. So we can apply the limit test. Okay. So now we have to calculate the limit of these terms. Okay. So this is equal to limit x tends to infinity, x as it is. We can write this, multiply and divide this bracket by x square. Okay, so we can write this as x square minus x square is 1 minus 1 upon x square. Similarly, divide this divider also. Divide numerator and numerator by x square. Okay, so we have divided numerator by x square. Now divide numerator also by x square. So x square minus x square is 1 plus 1 upon x square. Okay. Now, as x tends to infinity, 1 upon x square tends to 0. 1 upon x square tends to 0. So 1 minus 0, 1 plus 0. So 1 minus 0 is 1. 1 plus 0 is 1. 1 by 1. So this bracket is 1. But as x tends to infinity, this x also tends to infinity. And this is final term. But this is infinite term. This as x tends to infinity, this term goes to infinity. So total term goes to infinity. Okay. So here p is equal to 1 and limit L is equal to infinity. So the second case of the limit test says this integral is divergent because x is to the power p into f of x, the limit is infinity, p is equal to 1. So the test second part is if p is equal to 1 and limit is not equal to 0 and or equal to plus minus infinity, here limit is equal to infinity, p is equal to 1. So by limit test, here p is equal to 1 and limit is equal to infinity. So by limit test of convergence, this improper integral from 1 to infinity of x square minus 1 upon x square plus 1 with respect to x is divergent using limit test. Okay. Now we will solve this. So in this example, we have to show this integral is convergent using limit test. Now, since the integral is convergent, the value of p must be greater than 1, either it's equal to 2, 3 or anything. Okay. So here our function is x square into e raised to power minus x square. Is always continuous functions, so belong to class of continuous function for x 0 is less equal x less than infinity. Okay. So we can apply limit test because function is continuous. Okay. So we will calculate. Okay. So sorry, here question is to check the convergence of e raised to minus x square. Okay. So the question is show that the integral 0 to infinity of e raised to minus x square is convergent, and we know this function e raised to power x, e raised to power x square, e raised to power minus x square always continuous for x lies between 0 to infinity. Okay. So let's correct the question, please. Okay. The question is to show the integral e raised to power minus x square is convergent. Okay. Now to apply limit test, and we have to show the improper integral is convergent. So we know we calculate the limit of x raised to power p into f of x, and now we have to show the integral is convergent. So we have to take the value of p greater than 1. So either we will take 2. So we will first try for p is equal to 2. Okay. So now limit x tends to infinity x raised to power p, and we have to take p greater than 1. Why? Because we have to show the integral is convergent. So we will try to take p greater than 1. So we will take p is equal to 2. So x square into f of x. What is f of x? It is e raised to power minus x square. Okay. And limit x tends to infinity. Now we will change the variable. Okay. Instead of x, we will write t. Okay. So put x square is equal to t. This becomes limit x tends to infinity t into e raised to power minus t. But now instead of x, we have to take t. We are replacing x square by t. So this x square becomes t minus x square. So minus of x square. So minus of t. And as x tends to infinity, so here x square is equal to t. Okay. And as x tends to infinity, t also going to infinity. So limit t tends to infinity into e raised to minus t. This is nothing but equal to limit t tends to infinity. So e raised to minus t means 1 upon e raised to power t. Now as t tends to infinity, this infinity, this become infinity, e raised to power t also become infinity. So infinity by infinity. So we have to use here hospital rule. Okay, L'Hopital rule. So this equal to limit t tends to infinity. When there is infinity by infinity format, we have to take first derivative with respect to t and then take the limit. So derivative of t is with respect to t is 1, and derivative of e raised to power t is e raised to power t. Now as t tends to infinity, e raised to power t also tends to infinity, but 1 upon e raised to power t, e raised to power t tends to 0. So limit is equal to 0. Now here t is equal to 2 and limit is equal to 0 is a real number. So by part 1 of the limit test, what is limit test? Part 1. If limit is real number and p is a number greater than 1, then the integral converges absolutely. So by limit test, the integral from 0 to infinity of e raised to power minus x square dx converges. Okay. This is the application of limit test for convergence of the improper integral of type a. Okay. Thank you.